Hello, my name is Vito, and today we are going to take a deep dive into the networking of XRP Ledger. Specifically, my aim is to discuss core concepts of networking and peer-to-peer systems, node identity, peering protocol, and then finally, peer discovery. So this course assumes that you are familiar with standard networking concepts such as IP, TCP, and UDP. If not, I recommend going to read through these concepts first, and then afterwards join me where we'll go through the course. So with that out of the way, nothing to it but do it. Let's start. So, core concepts. We often hear discussions about or mentions of distributed and decentralized systems. So let's start with a definition. What are these systems? So in essence, the way to think about it, it is a collection of entities, usually servers, that are first and foremost autonomous. This means that each component, each server is running their own software, and they are taking actions based on their local state and or the messages they receive from the network. There is no central control unit that tells each entity in the system what to do. Each server makes their own decisions. Secondly, these entities are asynchronous, and this is one of the most crucial components of distributed or decentralized systems. By asynchronous, we usually mean that there is no central clock that dictates the same time for all instances, but rather all instances are running on their own time. Because of this, servers will require a way to decide what is the common truth. To do this, servers implement what you all know as consensus algorithms. However, this is not a conversation for today, so we'll leave consensus to another time. Thirdly, distributed systems are failure prone. Hardware fails all the time. Hard disks fail, network cards burn out, CPUs stop running, hardware is unreliable. At the same time, the networks are unreliable. Packets might be dropped, packets might not be delivered, packets might arrive in a different order than they were sent. The logic of the system must account for these failures and do its best to recover these faults. Finally, these systems, these servers, they are not physically connected. They communicate over the internet. As you may very well know, what we call internet is highly unreliable. This means that packets get sent in unpredictable orders, they might not be routed, they might be delivered multiple times. There are no guarantees made when the packet will be delivered in the first place. Again, all of these systems have to make accounts for these unreliable aspects. But, well, what is the difference between a distributed system and a decentralized system? Well, there are very good definitions for this. A distributed system is a networked computer system in which processes and resources are necessarily spread across multiple computers. In this particular case, necessarily means that the servers are distributed no more and no less to meet the current demands. So for example, take your favorite video streaming platform, Netflix, YouTube, Apple TV. They are not operating from a central server, meaning that when I press play, my request to load the video does not go to central server together with everybody else's requests. Instead, my request maybe goes to my local internet service provider, maybe goes to a local server running somewhere closer to me. By doing so, these services can support a better user experience, lower latency. On the other hand, decentralized system is a networked computer system in which processes and resources are necessarily spread across multiple computers. Necessarily in this particular case means that distributing the computers is necessary for the correct function of the system. So to give you a couple of examples, for example, IoT systems are distributed systems. So in your home, you have multiple sensors. Maybe one in your fridge, maybe one checking the temperature levels, maybe another one feeding your dog. Who knows? But for these systems to work correctly, they have to be distributed. It wouldn't make sense if they all were in the living room. They wouldn't be able to do their job. If you go a little bit more advanced levels, well, there's a concept called federated learning. Federated learning is in essence a machine learning paradigm where you have multiple institutions, multiple corporations that together want to build a single machine learning data model. However, what they do not want to do is share their private, sensitive, proprietary data. The way they solve this is by employing specific federated learning algorithms that allows these entities to teach a single model on the data without having to give up their data for central control. And finally, the example you know the best are distributed ledger technologies. Blockchains. For a public blockchain to work correctly, it must be distributed. Because if all of the instances of all of the servers of the blockchain are owned by a single entity, well, it loses its power of decentralization. Therefore, multiple parties have to own multiple servers. We can summarize this with a very simple table. So if we take a centralized system, let's say a regular database, the input for that database will come from multiple sources. However, all of the data will be stored on a single server. All of the processing of the queries will be done on the same single server. The output will come from the same single server. And of course, that server is controlled by a single entity. If you go towards distributed systems, now the input comes from multiple servers, the data stored is in multiple servers, the processing and the output come from multiple servers. However, this system is still owned by a single same entity. And finally, with decentralized systems, we add the final piece of the missing puzzle is where the system is now controlled by multiple different entities that may or may not trust each other. Before we jump into our next topic, let's give a little bit more context about what are we going to talk about specifically today. So there are two types of communications that happen in a blockchain. First are the client to server communication. This is RPC calls, WebSockets used by end users, such as me and you, to submit transactions or query the blockchain. On the other hand, we have server-to-server communication. These are TCP connections between the servers through which servers talk to each other, sending various control messages, passing consensus messages, sending newly or old submitted transactions, synchronizing with the network, and other necessary communications necessary for the blockchain. All right, we can move to the main topic. Let's discuss how the XRP Ledger peer-to-peer network forms. We have a couple of requirements. First, each server on the network must be able to uniquely identify itself. Second, servers must be able to establish secure communication channels between each other. And finally, the servers in the network must have the ability to connect to the network, find other servers to connect to. So how do they do this? Well, let's talk about node identity. So each server has to have a way to establish a unique identity in the network. And the way they do this is, first, when the XRP Ledger server starts up, it generates a unique public-private key pair. The public key acts as the identifier of the server. We use a base 58 encoding algorithm to encode the key, and then whenever the server needs to show its identity or prove its identity, it can do so by sharing this key. On XRP Ledger, there are two key systems. So each server in the network has a unique node ID. However, in addition, validators have an additional validator ID. This validator ID, while it is derived the same way as a node ID, it is an entirely separate set of keys. This identity of validators, it is then used to sign consensus messages that are originating from this validator. It is very important. There's no cryptographic link between the node identity and the validator identity. And users or operators that are running validators should take great care to never expose their node identity and validator identity together. It is okay to share your node ID. In fact, every time your server connects to another server, it will share its node ID. And every time your validator emits a validation message, a consensus message, it will emit its validator ID. But it's very important that the peers you are connected to do not know that your server is a validator. The reason for this is very simple: security. The moment a peer or another server in the network identifies which server is a validator, then they can launch various attacks against the server. Alright, so we covered identity. We know how that is created. We know that there are two identifiers in the system. Everyone has a node ID. Validators have a validator ID. Cool. So how do servers actually establish a connection? This is achieved through the peering protocol. It is a multi-step protocol that starts with a simple TCP connection. For now, for simplicity's sake, let's assume Alice knows the IP address of Bob. So Alice establishes an open TCP connection. As a second step, Alice and Bob upgrade that TCP connection using SSL TLS to make sure that nobody can snoop on their traffic. However, we still have a problem. How can Alice guarantee that the server it connected to is indeed Bob? And this is where node identity of Bob plays a role. The XRP Ledger uses a proprietary handshake to do two things. First, verify the identity of the other server that Alice peered to, in our example Bob. And second, ensure that there is no other malicious third party between Alice and Bob. The way this is done is by relying on internal SSL TLS protocol attributes that are called finished messages. Now, I will not go too deeply into what these messages are. I recommend you reading about it in the documentation of the SSL protocol. But in essence, this is a value that Alice and Bob can calculate, that you compute independently, and it is guaranteed that this value is going to be the same. So the way Alice can prove her identity to Bob is by first sharing her public key and the finished message signed with her private key. Then this allows Bob to take in this information and not only verify that the finished message was signed with a corresponding private key, but also verify that it is Alice who indeed has the other end of the connection. Similarly, Bob does exactly the same thing. He sends to Alice his public key, his version of the finished message signed with his private key, and this allows Alice to verify that indeed on the other side of the connection, it's Bob. So to summarize, the peering protocol handshake first it verifies that the other party is indeed who they claim to be, and secondly, it verifies that there is no man in the middle in their connection. So finally, how do servers discover other servers in the network? Let's talk about peer discovery. When I spin up my XRP Ledger server, I need to have a way to join other already run participants of the XRP Ledger. There are a couple of ways to do that. First, within the code implementation, there is a set of hard-coded so-called bootstrap nodes. These nodes provide initial access to the network to most participants. Secondly, node operators may provide either alternative set of IPs to the IP stanza to act as the bootstrap servers, or provide a stanza called IPs fixed. With this stanza, your server will attempt to and only connect to the servers that are provided in this IPs fixed stanza. If your server is not configured to maintain only a fixed set of peers, it needs to establish additional connections. So, of course, every server needs to maintain at least one outgoing connection into the network. However, remember that a distributed, decentralized system is communicating over an unreliable medium. So the only connection that I share with my peer may break at any point for no good reason. So each server in the network must have multiple redundant connections. For example, on XRP Ledger, when your server will start up, unless configured otherwise, it will attempt to find at least 15 other different peers to connect. On the other hand of the connection, some servers have to accept 0 or more incoming connections. In essence, an incoming connection is kind of a slot saying to the network, hey, I am willing to accept connection from other servers. The servers that accept incoming connections, in essence, serve as an access point to other participants into the XRP Ledger. XRP Ledger motto is often quoted as best incentive is no incentive. Therefore, the servers that are accepting incoming connections are acting altruistically. They do not necessarily receive any direct benefits for accepting connections. Although a server may accept an incoming connection, it requires a way to tell new joiners that, hey, here's an IP address that you can connect to that will be able to accept your connection. The way this looks on XRP Ledger is that each server with open incoming slots periodically sends advertisement messages to its peers. And this advertising message in essence says, well, at this IP address, you will find a server that has at least one incoming connection slot. This message also contains a hop counter. Every server that receives such an advertisement, first it caches it locally, and secondly it increments the hop counter and forwards it to its peers. If I try to connect the server that does not accept incoming connections, that server will terminate the connection, but in the termination message it will say, well, here is a list of alternative IPs I've heard from the network, you may try to establish more connections. Servers use 3 strategies when maintaining a connection to the network. First, fixed slots. So these are either the hard-coded addresses in the code, or the IP addresses provided in the IPs or the IP's fixed stanzas. These are the highest priority peers that a server will always attempt to maintain a connection to. The second stage is the live cache. Every time a server receives an advertisement, it caches it temporarily into the live cache. Of course, because the advertisements over time might become no longer true if the advertised server no longer accepts incoming connections, these entries are removed very frequently. However, if my server is missing connections, if it needs to establish more connections to the network, it will go into the live cache and connect to the servers there. And finally, we have something called the boot cache. The boot cache is the most interesting aspect. So imagine I was running a server in the network that afterwards crashed. I switched it off, it restarted, doesn't matter. That server, every time it connected to another, successfully connected to another good peer, it has cached its IP address in this long-lived boot cache. So when I start up, instead of restarting the discovery process, I will load the IP addresses from the boot cache and attempt to connect to them. The limitation with the boot cache is that although I was connected to that peer yesterday, that doesn't mean that I'll be able to connect to that peer today. So connection attempts to the IP addresses in that boot cache are likely to be met with a rejection. But as we discussed earlier, when a server rejects a connection, it sends me a list of other IP addresses from its live cache that it has heard about that I should try to connect. Alright, so that was a deep dive into the XRP Ledger networking. Let's summarize what we've covered. So first, each server in the network has a unique node identifier derived from the public key of that node. This identifier is then used to verify that the server is indeed who they claim to be. In addition to that, validators have a separate additional identifier that is derived from a completely separate set of public and private keys. This identifier is used to uniquely identify which validator produced which consensus messages. Secondly, when servers attempt to connect to the network, they perform a proprietary handshake. This handshake is there to first verify that the server that claims an identity indeed has the necessary private key to prove that they have the identity. And secondly, it ensures that the connection between two parties is secure, meaning that there is no man in the middle between the connections. And finally, we learned that the servers use bootstrap nodes to get initial access into the network and then use a peer discovery algorithm to find additional peers to connect in the network. So this wraps up our presentation for today, and thank you for your time.